computer. All right, well, let's get started, I guess they'll join us. So this chapter is going to be on sources of the magnetic field. Sources of the magnetic field. Now, in the last chapter, we assumed the presence of magnetic field, and then we're trying to find out the force on moving charges or current carrying wires and so on. Now, in this chapter, we're going to look the cause of magnetic field. The cause of magnetic field is current or motion of charges. So in this chapter, we want to look at the relationship between the magnetic field and the current or motion of charges. Okay. So first, let me state that if you've got a charge moving, let's say with a velocity v over here, the magnetic field on the line, which is, okay, so let's say you've got a charge q moving in this direction. Now the magnetic field in the line of action of that velocity is 0, okay? So magnetic field in the line of action of the direction of the velocity is 0. Let me say that, magnetic field in the line of action of the velocity, line of action of the velocity is 0. Maybe let me say over here, magnetic field due to moving charges. Magnetic field due to moving charges. Okay, so if you've got a velocity moving this way, the magnetic field at any point in the line in the direction of the velocity is 0, okay? Let's say your velocity is going this direction, then the magnetic field at all the points over here would be 0, okay? So let's say, how about if you have a charge q going in this direction and interested in the magnetic field at this point, okay? Let's say this is the point we're interested in. So this would be the position vector of the point with respect to the charge over here. Now this velocity, we know that the component of the velocity in the direction of the position vector is not going to have any effect, right? So we can drop perpendicular over here. So this would be v parallel, okay? And this would be v perpendicular, okay? So this component over here doesn't have any contribution to the field because of what we stated over here, right? If you take this velocity over here, the magnetic field due to this velocity at all the points in this line is 0. So that tells you the magnetic field depends only on the component of the velocity perpendicular to the position vector of the point with respect to the charge. Okay, so now let's look at the proportionalities. The magnetic field depends on the following factors. It is proportional to the charge. The greater the charge, the greater the magnetic field. It's also proportional to this, to the perpendicular component of the velocity. Okay, perpendicular component of the velocity. All right, and also depends on the distance. Okay, it's inversely proportional to the square of the distance. Let's say this distance over here is rp. Okay, it's proportional or inversely proportional to the square of the distance. This is true of any field. You take electrical force, is inversely proportional to the square of the distance. You take gravitational force, is proportional, inversely proportional to the square of the distance. That's, if you got something where it's spreading in all directions like this, you see, the area increases. The area increases with proportional to the square of the radius, and so the intensity of the field decreases proportional to the inversely the square of the distance. So these are the quantities upon which the magnetic field depends upon. Okay, so we can say this magnetic field is proportional to the charge times v perpendicular divided by rp squared. Okay, now let's look at the direction. Let's say the magnetic field will be the magnitude of the field times the direction of the magnetic field. Okay, now let's look at the direction of the magnetic field. Now, if you have a charge moving, maybe a current in this direction, let's say vertical over here, and then you put glass over here, as we saw last time in the experiment, and you put iron filings and shake it, you'll see that the magnetic field lines will be circular. Okay, they will be like this experimentally. Okay, so let's say we're looking at the charge moving over here, and then you've got a circle over here. That'll be the magnetic field lines. Okay, like this, because as you know, the direction of the magnetic field is the direction of the equilibrium of the particles or iron filings. So if you get circular lines over here, that actually gives you the direction of the magnetic field. So in other words, the direction of the field is in the direction of E phi. Okay, it's circular over here in the direction of E phi over here. Now, if you take this position vector over here, that is in the direction of the position vector, let's call it maybe ER, okay, like this. Now, how do you express it? Let's say you have the velocity in this direction, the magnetic, the magnetic field in this direction. Okay, let me draw a bigger one. So let's say we have the following. Let me make it diagram bigger. So we've got this circle over here. It's like this is the z-axis, and this is the x-axis. This is the y-axis over here like this. So you've got the velocity in this direction, and then the magnetic field lines are going to be circular like this. Okay, so that means the direction of the magnetic field is tangential to this one. Okay, so this direction over here, E phi, is perpendicular to both the velocity and this position vector over here. Okay, this is the direction of the position vector over here. So how do you relate this direction in terms of this velocity and this one? You see, this velocity over here is perpendicular to both the velocity and the position vector. Okay, so that means you can express this direction as a cross product between these two vectors. You see that? This is a circle over here. I don't know. You got a circle over here. This is the direction over here. You got the velocity going this way. You got the direction of the position vector going this way. So you can express it as a cross product between velocity and the position vector. Okay. So you've got position vector going this way. You got velocity going this way, and then this is tangential. You got a circle over here. That's E phi over here. So you can express the direction of the magnetic field like this. It is parallel to this vector B cross the position vector RP, okay? Because it's perpendicular to both of them, okay? If you take a tangential vector over here, it's perpendicular both to the velocity and to the position vector. So that means the direction is parallel to this cross product. Well, I should say it's just not the, well, it's parallel to this one. But then the unit vector is like this. You take this cross product, RP over here, and then you divide by the magnitude of this one. Okay, so that will make it a unit vector perpendicular to both of them, to the position vector and to the velocity vector. Okay, all right, but what is this? V cross B plus RP. By definition, the magnitude is V RP times the sine of theta. Okay, it's a cross product, but V sine theta is simply the component perpendicular to the position vector, V perpendicular. Okay, so we can write this magnitude over here, V cross RP. We can write it as the velocity times sine theta would be V perpendicular, and then you've got RP over here. All right, so the unit vector in the direction of the magnetic field is this one. You have V cross RP over here, divided by the magnitude, which is V perpendicular times RP. Okay, so now we're going to put the direction with the magnitude. All right, so the vector value of this one is, you guys, proportional to charge, proportional to the perpendicular component velocity, and well, still I'm saying proportional. And then we have RP squared over here. Okay, that's from the magnitude. And then for the unit vector, we have the following. This is the unit vector, R cross B divided by V perpendicular RB. So the unit vector is V crossed with RP divided by V perpendicular times RP. Okay, so you see the V perpendicular cancels out. So we get this relationship, charge, and then V cross the position vector divided by the cube of the distance between the velocity and the point. Okay. Now the constant proportionality is mu naught over 4 pi. So now we can change it to equality. The constant is mu naught over 4 pi. Okay. So you've got the following formula: Q V cross the position vector RP divided by RP cubed. Okay. So this is a formula for the magnetic field due to the velocity is proportional to the charge is in the direction of V cross P. All right. So let me try to put this in a form of a diagram. Let's say you have this charge over here, the charge Q over here. Let's say it's moving in this direction. That's my velocity vector. And I'm looking at the magnetic field at this point. Let's call it point P. All right. So this is my RP, the position vector of the point with respect to the location of the charge. All right. So it is V cross RP and then divide by the distance or the magnetic position vector cubed. Okay. That's the meaning of this one. All right. How about if we have arbitrary, we're assuming the origins over here, but let's have an arbitrary origin over here. So let's say the velocity is located over here and it's going this way, and we're looking at the magnetic field over here. Okay, so the position vector of this one of the point, that's called R. The position vector of this one of the charge, that's called R prime. Okay, this one, which is RRP, this vector over here, which is RRP, is R minus R prime. Okay, so if the position vector of the point is R, the position vector of the charge with respect to an arbitrary coordinate system is R prime, then this vector over here is R minus R prime. Okay, and RP also will be the magnitude of R minus R prime. Okay, so with respect to an arbitrary coordinate system, we can write the formula as follows: the magnetic field equals the constant mu naught over 4 pi. We got the charge, and then you've got V crossed with R minus R prime divided by the magnitude of R minus R prime cubed. Okay, so this is the general formula. Do you remember the value of the constant mu naught? We used it in the lab. Do you remember the value of this one? Mu naught. This is called magnetic permeability of vacuum. This is magnetic permeability of vacuum. Permeability of vacuum, and its value is 4 pi times 10 to the power of -7. Okay, it'll be Tesla, I guess, meter squared. I mean, yeah, and then divided by meter per second, something like this. So it'll be Tesla second meter, something. Okay, so this is the general formula for the magnetic field due to a moving charge. Okay, so you've got a charge moving this way, the magnetic field over here is given by this formula. All right, now let's consider an example about how to apply this formula. Okay, let's look at an example. Okay, let's have a coordinate system. Let's say this is my coordinate system over here. Okay,
so can you move the paper a little bit?
Oh, I'm sorry. Let me fold this like this. All right, so suppose, let's say at x equals to over here, I have this charge. Okay, so this is x equals to, and it's moving, let's say, with a velocity of 100 meters per second, let's say, and this is x equals to. All right, and then let's say I want to find the magnetic field over here. Okay, let's say I want to find, this is my point P over here. All right, let's say the coordinates of this point are, I don't know, maybe, let's say maybe 4 and 3. Well, let's say it's, okay, does it make sense? I got 4 and then maybe 5 on this side. Okay, okay, suppose these are the locations of this point. Okay, and let's end the charge also, let's say it is maybe 2 microcoulomb. Okay, this is our charge. All right, now let's apply this formula to get the magnetic field at this point. So all we need to find is these vectors. Okay, so I've got the velocity vector in the I direction. Okay, so I've got the velocity vector. The velocity vector is 100 meters per second in the I direction. Okay, and then I'm going to need these two vectors. This is my R prime over here, and this is my R, the position vector of the point. Okay, so this is my R, this is my R prime. All right, so my R is 4 in the I plus 5 in the J. Okay, this is my position vector for R. How about R prime? R prime is simply 2 in the I direction with respect to this origin, right? So this is R prime is 2 in the I direction. Okay, so what I'm going to need is I'm going to need this vector, which is R minus R prime. Okay, that is 4I plus 5J minus 2 in the I. Okay, so my R minus R prime is 4 minus 2 is 2. That is 2 in the I plus 5 in the J. Okay, I'm also getting the magnitude of R minus R prime. Okay, that's going to be square root of 2 squared plus 25 squared, 5 squared, 25, right? And that's going to be square root of 29. Okay, and then what I'm going to do is V crossed with R minus R prime. Okay, so this equals, this is 100 in the I crossed with R minus R prime, which is this one over here, which is 2 in the I plus 5 in the J. Okay, so let's just cross product. What is I cross I? Two identical vectors, 0. And I cross J?
K.
I cross J is K, okay? So we just have 100 times 5, that's 500 in the K direction, okay? So pretty much have everything I want. Now let me write the formula. So we get mu naught equals mu naught over 4 pi, okay? And then I've got V cross R minus R prime, okay? Divided by the magnitude of R minus R prime cubed, okay? So that is 4 pi times 10 to the power of -7, that is mu naught over here, divided by 4 pi, okay? And V cross R minus R prime is 500 in the K direction, right? And then the magnitude of R minus R prime cubed, which is this one, you've got 29 cubed, okay? And the direction of the field is in the K direction. See that? So that's how we calculate the magnetic field over here. So that means the magnetic field over here is perpendicularly out. You see that? It comes out, it's K. This is J, this is I, and the direction of the magnetic field is perpendicularly out of the paper. All right? So that's how this formula works. Magnetic field due to moving charge is given by this formula. All right? Now we're going to generalize this to magnetic field due to current. Okay? So let's generalize this to magnetic field due to current. So let's generalize this to, let him in. Okay, now we're going to look at magnetic field due to a current carrying wire. Okay. So let's say you have this wire over here carrying current, let's say I, okay? And we want to find the magnetic field at this point. Let's say it's my point B, okay? So this is motion of charge over here. So at every point, you've got charges moving. So what we can do is we can find the magnetic field with small charge dq over here, okay? We take a small charge dq over here. We obtain the magnetic field due to this charge, and then we integrate, okay? So let's find the magnetic field due to this charge over here, all right? Let's call it dB, all right? The magnetic field let's say this be magnetic field B due to dq, d to dq, and then we're going to integrate. Okay, so we can say that this is the formula for moving charges. We have already established that formula. That is mu naught over 4 pi and v crossed with rp, okay, divided by rp cubed. This is, and then there's a charge dq over here. There's a charge dq over here. All right. So, well, this is our rp, the position vector of the point with respect to charge. This is our rp. All right. Now, suppose this path element over here is ds. The small path element, let's call ds, this path element over here. So the velocity at that point is displacement, the displacement ds over here, divided by time. Okay, this is the velocity over here. All right. So with that, let's write this again. So you've got the following: dB, the magnetic field is this charge element over here. And this location is a constant mu naught over 4 pi. We have the charge dq. Now I'm going to replace the velocity. The velocity is displacement per unit time. If this displacement is done in a time interval dt, then this will be ds divided by dt. Okay. And then we have the cross product with the position vector over here. And then, of course, divide by the distance cubed. Okay. Now let's rearrange this one over here. Okay. dq ds by dt. For dq ds by dt, let me write it again. So this would be dB equals mu naught over 4 pi. Now you see, I'm going to put the time under dq like this, dt. And then I've got ds over here, and then cross it with rp and divide by rp cubed. Okay, this is it. I just took the dt from here to here. But what is dq by dt? The rate of flow of charge. What is that?
Current.
Current, very good. But dq by dt, the rate of flow of charge, is current. Okay, so we have the following. This magnetic field is this small charge element is mu naught over 4 pi. We got current over here, and then we take ds, cross it with the position vector, divide by the magnitude cubed. Okay, so this is the magnetic field due to this small charge element over here. Due to this small charge element over here. To get, we can do that for all the charge elements over here. Okay, and then all I have to do is add up or integrate. Okay, so the total magnetic field, which is B at that point, is going to be the integral of dB, which is, we can take the constant out, mu naught over 4 pi. Also, we're going to deal with constant currents over here, and then you get the following: ds cross rp divided by rp cubed. Okay, integrated over the wire. All right, this is it. So this formula is called the Biot-Savart law. Okay, so let me write it again. The magnetic field is mu naught over 4 pi times current, and the integral of ds crossed with rp divided by rp cubed. This formula is called Biot-Savart law. Biot-Savart law. All right, now let's talk about direction. Now, you see this ds over here, you can integrate it from here to here. You always integrate in the positive direction. If the current is flowing the opposite direction, we're going to put the sign on the current, okay? Do this integral in the positive direction. What this means is, if you're doing a horizontal integral, it'll go from left to right, okay? If you're doing a vertical integral, it'll go from down to up. If you're doing a circular integral, it'll go in a counterclockwise direction. So do this integral ds over here always in a positive direction, either right, up, or counterclockwise, okay? We're going to put the sign on the current, okay? So the current will be positive if it's going in a positive direction. It's going to be negative if it's going in a negative direction. Okay, so we're going to put the sign on the current, but we'll do the integral in a counterclockwise direction. All right. Or if you want, you can also use the absolute value of the current over here and then put the direction on ds. You could be going either from lower to higher or higher to lower, depending on the direction of the current. Okay, you can do that too. But I think it's easier to do this always in the positive direction and then put the sign over here. If the current is going, for example, counterclockwise, you make it positive. If it's going clockwise, make it negative. All right. All right. So we're going to look at some applications of this formula now. First, we're going to look at magnetic field due to a straight wire, a current carrying straight wire on the line of the wire itself. Okay, let's look at magnetic field. Magnetic field due to a straight current carrying wire, current carrying wire on pointers that lie on the same line as the vector, that lie on the same line as the wire, the same line as the wire. Okay, but that what I mean is, let's say this is a current over here. Okay, let's say we have current flowing over here. We want to calculate magnetic field at the same pointers, at the points that lie at the same line as a wire. Okay.
I'm so sorry. Could you adjust the paper again?
Sorry. Thank you for. Please let me know if I do that. I don't know why I'm pulling it. All right. Maybe I should hold it like this. All right. So in this section we're looking at is the magnetic field for points that lie in the same line as the wire. Okay. So let's say if you take a charge dq over here. Okay. So what is RP? RP is this one over here. This one over here, right? This would be my RP. How about DS? DS is also this one over here. The direction of DS is this way. Okay, they're both in the I direction. They're parallel. So DS is parallel to RP. So what's the cross product? They're parallel.
0.
0. Therefore, this implies DS cross RP is 0. And that implies the magnetic field is 0. Okay, so the field, the straight wire, at all pointers that lie in the same line as the wire is 0. Okay, so that's the conclusion over here. The magnetic field at any pointers on the same line as the wire is 0. All right, now we're going to look at magnetic field due to an arc at the center of the arc. So we're going to say, maybe on the other side over here. We're going to look at magnetic field due to a current carrying arc, at the center of the arc. At the center of the arc. Okay, so that's what we're doing. Let's say this is my coordinates over here. So we're talking about an arc like this. Okay, let's say it's a complete circle over here. We want to calculate the magnetic field in this arc at the center of the arc. Okay, so, well, we're going to take our ds over here. This is my ds over here. Let's say it's carrying a current I. Okay, let's say it's going counterclockwise like this. So this is ds. Now remember, this is my RP. I'm trying to calculate the magnetic field at this point, right? So what do you think is the position vector of this one?
0.
0. So this is my R, this is my R prime, okay? So this is r prime over here, and r is 0. R is 0, but r prime, let's say the radius is r, okay? Let's say the radius of the arc is r over here, all right? So r prime is r in the direction of, you remember this unit vector over here? We used to call it e theta, but let me call it e phi, okay? So this is e phi. The unit vector in the direction tangent the circle is e phi, okay? You remember those unit vectors? You remember these unit vectors? We have er equals cosine of theta in the I plus sine theta in the j, which is the radial unit vector. And then we had e theta equals negative sine theta in the I plus cosine of theta in the j, which is tangent to the circle, okay? So that's what we're talking about over here. So this position vector over here, r prime, I can write it like this. If this angle over here is phi, if this angle over here is phi, then I can say this is r, and then this vector over here will be negative sine phi in the I direction plus cosine of phi in the j direction. Okay? No, I'm talking about ds. This is radial. I'm sorry. I'm talking about ds over here. This is not r prime. This is in the radial direction. I'm talking about ds. So ds over here is its length ds in the direction of e phi. Okay? This ds over here, it's magnetic ds, and its direction is e phi tangent to the circle. Okay? So that will be ds, and e phi is negative sine phi in the I direction plus cosine of phi in the j direction. All right, so that's my ds vector. How about this vector over here? This vector over here is the direction of er. Remember that? So this r prime over here, if the radius is r, this is r in the direction of the radius. Okay, like this. So this is r, and then you've got, this is cosine of theta in the I, sine theta in the j. In this case, it will be cosine of phi in the I direction plus sine of phi in the j direction. Okay, so these are our vectors. This is r prime, r is 0 because we're trying to calculate the magnetic field at the origin. Okay, so let's look at what we need. We need, first of all, we're going to need r minus r prime. Okay, so r minus r prime is going to be 0 minus this vector over here. Okay, so this is 0 minus, this is cosine of phi in the I direction plus sine of phi in the j direction. Okay, and there is r over here. So, all right. So this is my r minus r prime. So it's basically negative r cos phi in the I direction minus r sine phi in the j direction. R minus r prime. Okay. Now let's do the magnitude of r minus r prime. The magnitude of r minus r prime would be square root of the square of negative r cosine of phi squared, and then the square negative r sine phi squared. Okay, so we can take r out. Square root of cosine square of phi plus sine square of phi. So what's the square cosine square of phi plus sine square of phi?
1.
1. So it's just r. So our magnitude is the radius of the circle. All right, and then what we're going to need is this one, ds crossed with r minus r prime. We're going to need this cross product, so let's do it. Okay, so what's ds? Ds is over here. It is ds in the direction of e phi, which is this one, right? So this is ds negative sine phi in the I direction plus cosine of phi in the j direction. We can cross it with r minus r prime, which is this one. Okay, so you've got negative r cosine of phi in the I direction minus r sine phi in the j direction. Okay, let's do cross product. First, let's distribute this. I cross I is 0, right? And then you've got I cross j. I cross j is k, right?
Okay.
And then you've got negative times negative is going to be positive, all right? So from this one, we get the following. From the, well, I'll put over here, ds. From this, you get only from this term over here. So you've got ds, you got r over here. Then sine phi times sine phi is sine squared phi. That is in the k direction, okay? Now let's repeat this one. J cross j is 0. We have only contribution from this one, okay? And what's j cross I?
Negative k.
Negative k, okay? But positive over here, we've got minus over here, so it's going to be positive, right? So plus, again, dsr and cos squared phi. Cos squared phi in the k direction. You see that? Okay, so both in the k direction, so we can add them together. Well, I factor out ds, so I'm to keep writing over here. I factor it out, okay? So we have the following. We get ds times r, and then k is a constant. I mean, we can factor it out. And then you've got sine squared phi plus cosine squared phi. What's this one equal to?
1.
1, okay? So this cross product over here, ds crossed with the position vector r minus r prime is ds r, and then just in the k direction, okay? In the k direction. All right, now let's express ds in terms of d phi. So this is ds, this is d phi over here, okay? This is d phi. How are they related? Do you remember? You've got a circle over here. This is s, this is r. This theta over here is s over r in radians. Do you remember that? So d phi is simply ds divided by r. Arc length divided by the radius gives you the angle, okay? So let's replace that. So we have bat ds equals r times d phi, okay? So we're going to replace this one. ds is r times d phi. So you've got this cross product. R minus r prime is ds, oh, I changed this one to r d phi. So it's going to be r squared d phi in the k direction, okay? That's my cross product. So I've got everything now. I can go to my integral now, okay? My integral is b is mu naught over 4 pi times the current, the integral of ds crossed with r minus r prime divided by r minus r prime cubed. All right, so let's substitute the values. This is mu naught current divided by 4 pi, okay? The integral of this one over here, which is r squared d phi, k is also constant, we can put over here, divided by this cubed. We've already done the magnitude. The magnitude is where? So over here, just r, all right? So it's r cubed over here, all right? So the integral is mu naught I over 4 pi in the k direction. We can also take r squared out. So, well, this is 1 over r, okay? So let me put r over here. So just the d phi, okay? So from where to where does this integral goes? You see, let's say this angle over here is, let's say 5 prime, and let's say this angle, the whole thing is delta phi for the arc length, okay? So we'll go from 5 prime maybe to 5 prime plus delta phi, okay? Let's say this angle is phi and this one is phi delta phi. In other words, this arc length over here is delta phi, okay? So I'm going to go for the arc length, I'm going to go from 5 prime to 5 prime delta phi, right? So this just gives me delta phi, all right? So we have the following. So this is mu naught over 4 pi r, all right? And then we have current over here, and this will just give me delta phi in the k direction, okay? So that's the magnetic field at the center of this arc, okay? This is the angle for the arc, all right? So let's consider an example for this one. Okay. Example. Now I should say this current over here is taking me positive for counterclockwise, negative for clockwise. Okay. So let me state that I is positive for counterclockwise, and is negative for clockwise. Okay. Usually in physics, counterclockwise positive, clockwise is negative. Okay. So suppose we have the following arc, just this one. Let's say the radius over here is 2 meters, and let's say the current over here is maybe 10 amps. Okay. I want to calculate the magnetic field at the origin. Okay. The question is calculate B at the origin. Okay, so in this formula, all I need is the current, delta phi, and R. Okay, so the current is 10 amps, we're told, and it's going to be positive because counterclockwise. Okay, positive over here, positive 10 amps. The radius is 2 for this circle. Can you tell me what's delta phi for this arc?
Pi over
Pi over 2, very good. So delta phi is pi over 2. All right. So the formula for this one is mu naught over 4 pi. We've got current. We've got delta phi. We got the radius over here in the k direction. Okay. So we have 4 pi times 10 to the power negative 7 divided by 4 pi. The current is 10 amps. Delta phi is pi over 2. And then divide by the radius, which is 2. Okay, in the k direction. So this is the magnetic field at the center due to this arc. Okay, now we're going to look at the magnetic field due to a complete circle. Okay, magnetic field due to a complete circle, due to let's say a current carrying circular wire, current carrying circular wire at its center. Okay, so in this case, we have this wire over here, and we have current flowing over there. Okay, let's say the radius is R over here. Can we use this formula to calculate it? Can you obtain the formula for a complete circle from this one? The only thing you have to find out is delta phi. What's delta phi for a complete circle?
2 pi.
2 pi, that's all you have to do. So for this one, delta phi equals 2 pi. Okay, so that's all I have to do. So the magnetic field is mu naught over 4 pi times current times delta phi divided by R. Okay, so for a circle, delta phi goes to 2 pi, and we have the following formula. B at the center of the circle is mu naught over 4 pi, the current, and then 2 pi divided by the radius. Okay, so you see, this is 1, this is 2. All right, so the magnetic field in a complete circle is mu naught I divided by 2R. Okay, usually we're going to deal with coils. If there are n turns, then it just multiplies by n. Okay, so let's put it like this. And if there are n turns, then you just multiply by n. Okay, so the formula would be B mu naught over 4 pi n over here, and then you got current over here. Oh, it's just 2R. We just multiplies by n. Okay, so it's going to be mu naught n. This is mu naught n I divided by 2R in the k direction. Okay. So this is the magnetic field at the center of a current carrying circular wire. If you remember, when we calculated the magnetic field due to a coil in the lab, we used this formula to calculate at the center of the coil, okay? So that's how we obtained it, all right? So now let's look at an example. Suppose, let's say we have the following, let's say we have this wire, maybe another wire like this. It's in the same line over here with this one. And we want to calculate the magnetic field at the center. Let's say we have the current going this way. The current is, let's say, 2 amps going this way. Let's say this radius is R. Let's say this radius is maybe 3.5, and this radius over here is, let's say, 3 meters, 3.5 meters. Okay, and the question is calculate the magnetic field at the center. Okay, calculate the magnetic field at the center. Magnetic field at the center. All right, now we have 4 contributions. We have current, field due to this wire, we got field due to this one, we got field due to this one. All right, can you tell me the field due to this wire over here, the straight wire over here? You remember the first thing we said? The magnetic field for points that lie at the same line as the wire is 0. Okay, this point lies at the same line as this wire over here. So the magnetic field of this wire over here is 0. The same thing with this one. This wire over here lies at the same line as the wire. This point lies at the same line as the wire. So no contribution from these two because of that. Okay, we have contribution over here only from this two. So this current is going to go this way. Okay, so in this wire, the current is going counterclockwise, but in this wire, it's going clockwise. Do you see that? So the current is going to be positive for this one. That's going to be negative for this one. Okay, so the current for the outer wire is clockwise. So the current is going to be 2 amps for that one. 2 amps, okay? Positive, 2 amps. The current for the inner semicircle is going to be negative 2 amps. Okay, so you've got 2 fields over here. The net magnetic field is B due to the outer wire plus B due to the inner wire. Okay, so what is the outer wire? Well, we have this mu naught times the current outer over 2 times the radius of the outer. Okay, and that's in the K direction over here. And for the inner is mu naught times current for the inner divided by 2 radius for the inner wire. Okay, so let's just plug in the numbers. If you want, we can factor out mu naught over 2. So you've got mu naught over 2. So you've got I for the outer semicircle divided by the radius, also K over here, radius for the outer, and then you've got current for the inner divided by the radius for the inner. Okay, all right, what are the radiuses? Radius for the outer is 3.5, right? This one over here. So radius for the outer semicircle is 3.5. The radius for the inner is, I think, 3 meters. Okay, we got 3. That's it. So we just plug in the numbers. So you've got 4 pi times 10 to the power negative 7 divided by 2 in the K direction. The current for the out is counterclockwise, 2, divided by the radius of the out is 3.5, okay? Now the current for the inner is clockwise, so it's going to be -2, okay? And its radius is 3. Do you see that? So you have
Do we not need to divide it to account for the semicircle as opposed to the full circle for each?
Oh, you're right. There is pi over there. Delta phi is pi. You're right. That's a good point. So delta phi is pi. So we're going to divide by 2. You're right. I was doing it for complete circle. So there is pi. There is pi over here.
We just need to change the 2's
Well,
and the denominators to 4's,
yeah,
right?
you just divide by 2 because all we're doing is you have to use this formula over here. Where is the delta phi? We have to use this formula and we have to put pi over here. Okay, so this instead of 2 is going to be 4. We're going to divide by 2. This is so you're going to have to use this formula, and this one is going to be pi for a semicircle. Instead of 1 over 2, we're going to have 1 over 4. You're right. Thank you. I was doing it for circles. You're right. So the difference is going to be, this is going to be 4. It's going to be 4, okay? It's going to be 4. So that gives you the magnetic field at the center, okay? Now, the direction of the current and the direction of the field are related by the right-hand rule, okay? If this is current, this gives you the direction of the field, okay? So look over here. You see for this one, for the outer circle, is going counterclockwise, the direction of the field is a positive k. But this one is going clockwise direction, it's a negative k, okay? So that's another way of finding the direction. If you want, you can put the sign on the eye, make it positive, if it's counterclockwise, negative clockwise, or you find the magnitude by doing absolute value, and then you figure is positive k or plus k using the right-hand rule, okay? If this is the current, this gives you magnetic field, gives you time gives the direction of the field. So maybe let me say direction of field and current are related by the right-hand rule. Are related by the right-hand rule. Okay, we did that for solenoid last time, if you remember. So fingers represent current. Fingers represent current. Then thumb will represent field. Okay, so another way of doing this is you can just do the magnitude by putting the current in absolute value, and then you can turn the direction using the right-hand rule, whether it's perpendicularly out or perpendicularly in. Okay, or you can just make it positive or negative depending on whether the current is clockwise or counterclockwise. All right. So that's how we calculate the magnetic fields due to circular loops. Okay. Now we obtain current on the axis of a circular wire carrying current. Okay. Magnetic field on the axis of a current carrying circular wire. Current carrying circular wire.
Could you move the paper one more time?
Oh, I don't know. Should I put something in here? Let me hold it like this.
I think it's just because you're right-handed, it just keeps drifting.
Yeah, you're right. Just remind me if I do that. Okay, magnetic field on the axis of a current carrying circular wire. So let's say we have this axis over here. So let's say it's the z-axis. This is the x. This is a y. Okay. So let's say we have a circle over here, maybe of radius r. Okay. So we want to calculate the magnetic field on the axis of the circle. Okay. All right. So let's say this is z over here. Okay. And let's say this is r over here. All right. Okay. So we're going to take our ds. Let's say my ds is over here, part of the wire over here. Okay. Let's say it's carrying current maybe in this direction like this. So this is my ds. Okay, the same thing as we did before. ds is ds in the direction of the tangential in vector e phi, right? This tangential vector over here to e phi. And we know that that is this angle over here. I should put over here. Anyway, the phi is measured from here, from the x-axis. Okay, I should put over here, but anyway. So this is negative sine phi in the I direction plus cosine of phi in the j direction. Okay, if you take your ds to be over here, so this would be my position vector and this would be my phi. Okay, all right, so this would be the tangential in vector e phi over here. All right, and then of course, this is ds over here, this is d phi equals, or ds equals r d phi. Okay, we have ds equals radius times d phi. The arc length divided by the radius gives you the angle d phi. Okay, so we can write this one over here. This ds over here is r d phi. This is the r d phi. We're talking about the ds over here. Okay, will be negative sine phi in the I direction plus cosine phi in the j direction. Okay, so we have ds. And then we're going to need the position vectors. Okay, this is my point, right? So this is my r. This position vector is my r. So my r is simply on the z-axis. It's z in the k direction, right? The position vector of this point over here is z in the k direction. So my r is z in the k direction. Okay. How about this position vector over here? Okay, is in the radial direction. So we have the r prime. R prime is the position vector of the charge sample we're taking. Okay, so that is it's going to be the radius, and its direction is in r perpendicular direction. Okay, and we know that that's r, and that is cosine of phi in the I direction plus sine of phi in the j direction. Okay, this is the sinus vector over here. The sinus vector, let's go this way, radially outward. All right, so that's my r prime. So let's do now r minus r prime. We're going to need this one, r minus r prime, that's rp, equals z in the k minus r cosine phi in the I minus r sine phi in the j. Okay, so this, we're going to need this one, and then we're going to need the magnitude, right? So the magnitude of r minus r prime is square root of, we got d squared over here. From this we get r squared cosine squared phi. From this we get r squared sine squared of phi. Okay, so these two, they just add up to r squared, right? So this is simply square root of d squared plus r squared. So that's my magnitude for the, it's basically this line over here. Remember, RP is the distance between this and this. So it's simply r squared plus z squared. All right, and then we need the cross product. The cross product is ds crossed with r minus r prime, right? So let's write ds. So this is, we start with ds. ds is r d phi, and then we have negative sine phi in the I direction plus cosine of phi in the j direction. Okay, and then we can cross it with this vector over here, which is z in the k minus r cosine of phi in the I minus r sine of phi in the j. Okay, so let's do this cross product. So what is I cross k?
Negative j.
I cross k is negative j, but we have a negative over here, so that's going to be positive, right? So we're going to have, let me still keep the RD phi outside. This is going to be common. r d phi outside. Okay, so from these two, I get sine phi z in the j direction, right? How about this cross this? That's 0. I cross I, right? And then what's I cross j? I cross j is k, right? So I've got negative over here, negative is going to be plus. So you've got plus r sine squared phi in the k direction, right? Now let's do the same thing for this one, for the j. What is j cross k?
I.
I. Okay, so I'm going to have, we're doing now this one and this. Which one am I doing? Okay, oh, this one, this one. Okay, j cross k is I. So I've got z over here and then cosine phi over here. So plus z cosine of phi and j cross k is I. Okay, and then we do this too. You see, what is j cross I?
Negative k.
Negative k, right? You've got a cos squared phi over here. It should be, I think, so yeah, negative k, but there's a negative over here, okay? So they're gonna be positive, right? So that's plus r cosine squared phi, and direction is k, right? Okay, j cross j is 0. So that's what we have. So you see these two, what do you get from this?
1 or r.
Actually, there are r's over here, so it's going to be squares over here. Okay, this is square over here, square over here. All right, so it's just be r square, right? Because we have r over here and r over here. Well, the r is outside anyway. It's going to be square eventually. Let me take this off. All right, so let me write it in detail over here. So this is my cross product. So ds crossed with r minus r prime in this one. We have an I component. This is my I component, which is zr cosine of phi. I've got zr d phi cosine of phi, right? So this is zr d phi cosine of phi in the I direction. And then I've got a j component. This is a j component. It's r d phi z sine phi, okay? So r, well, zr d phi sine phi in the j direction. And then we have the k component. You see? That is, well, let's add them together. That's r squared, and there is d phi also, d phi over here. Okay, d phi, r squared phi plus d phi r squared cosine square of phi. This is in the k direction. Okay, so these two simply add up to r squared. You see that? It's simply r squared d phi. Okay, so let's go to our integral now. This is b. It is mu naught over 4 pi current times the integral of ds crossed with r minus r prime divided by the magnitude of r minus r prime cubed. Okay, so now we have 3 components, I, j, and k. Okay, so let's write like this. So we've got mu naught I 4 pi, and we have also the magnitude. This is our magnitude over z squared plus r squared. Okay, so that also will come out. The integral is over d phi. So you've got z squared plus r squared over here. All right. Okay. Now we have the following. We have an I integral, which is this one. Zr d phi cosine of phi. Okay, this is Zr d phi cosine of phi. We've taken the well, this is cubed. This is cubed. All right. So that's in I. And then we have j, the same thing. What is j? This is zr d phi sine phi in the j direction. And then we have the k part. The k part is r squared d phi. Okay. So when you add these ones, sine squared, that's what you get, okay? d phi. All right, now this is basically the integral of cosine. And this is a complete circle, the integral of complete circle, right? So 0 to pi, 0 to pi, 0 to pi. Okay? So what's the integral of cosine phi from 0 to pi? The integral of cosine is sine, right?
Which would be 0 at 2 pi.
0. So this would be sine. If you take it from 0 to pi, this would be 0. The same thing over here. You've got sine phi. We integrate it. It's proportional to cosine phi. If you take that from 0 to pi, that's 0. Okay? This goes away. So that's all you have. And when you integrate this one, you just get 2 pi times r squared. Okay? So, and that's in the k direction, So this is a magnetic field over here. We have mu naught I over 4 pi. And then from this, we just get 2 pi r squared, right? And then you got this distance over here, which is d squared plus r squared, 3 over 2, okay? The distance squared, and that is in the k direction. Do you see that? So let's simplify this by 2 pi 1. This one is 2, okay? So let's simplify, let's write in simplified form. This is a magnetic field at the axis of the cylinder, okay? So we have the following formula for the magnetic field. It is mu naught over 4 pi for our constant. We have the current, okay? And then we have r squared over here, r squared. And then we have the distance cubed, which is z squared plus r squared, 3 over 2. This is d squared plus r squared, 3 over 2, because the square root cubed, okay? And then the k direction. All right, you see that? Oh, I simplified this, I forgot. This is 2, this is 2. I simplified it, this is 2 over here. This is 2 pi by 2 pi, that's 2, okay? Now, let's check the formula for at the center of the circle. Where is that, right? At the center of the circle, what's the value of z?
0.
Okay, so at the center, z equals 0. So b at the center, using this formula, would be mu naught I r squared 2, and then you put 0 over here, it will be r squared 3 over 2, right? So you get mu naught I r squared over 2r cubed, okay? And then you get mu naught I over 2r. Let's compare that with the formula we had before. At the center of a circle, we just did that a while ago. Direction. Yeah, it's this one, perimeter by n. You see? This is what we got for the magnetic field at the center using this situation over here. And then for the magnetic field axis, generally, we got this formula at z on the axis, but if it's 0, we get the same answer, okay? So you can use this formula to calculate the magnetic field on the axis of a circle, at any point on the axis of a circle. So one thing I'll mention is, even though we've said k over here, generally, well, it could be like this. You can see me. The circle could be like, could be in any orientation. In that case, it's generally the direction of the area, EA. So instead of k, you can put EA over here. For any orientation, the direction of the field is in the direction of EA, which is the direction of the area. Okay, so this gives you magnetic field on the axis of a circle. All right, so this is its value on the axis. This is the radius of the circle. That's it. The current. That's all you need. In this case, also, the direction of the current and the direction of the field are related by right-hand rule. Okay, if it's counterclockwise, will be perpendicularly out. If it's clockwise, will be perpendicularly in. But what you can do is, if I is positive, counterclockwise, you can make it positive, so you get plus k direction. And if I is clockwise, you make it negative, you get negative k direction. Okay, but if you want, just do the magnitude of this one, and then use the right-hand rule. If it is clockwise, you get k. If it's clockwise, you get negative k. Okay, so whatever you want. All right. Next, we're going to look at the magnetic field and the perpendicular bisector of a straight current carrying wire. So this magnetic field at the perpendicular bisector of a current carrying straight wire. Current carrying straight wire. Okay. Suppose, let's say this is our coordinate system over here, like this. Let's say this is Z, X, and Y. Okay. Now, suppose our wire goes. Suppose this is our wire. This goes from, let's say, from negative B on the Z-axis to B on the Z-axis. Okay. So that means all the points on this plane, on the XY plane, are on the perpendicular bisector. Okay. You've got half of the wire up, half the wire down. All these points are located on the perpendicular bisector of the wire. Okay, so all points on the XY plane, if this is between B and negative B, are points on the perpendicular bisector. Okay, so let's say all the points on the XY plane, this is Y, the points on the XY plane are on the perpendicular bisector. Or I can say XY plane is the perpendicular bisector. Let me, it's easier. The perpendicular bisector is the XY plane. Perpendicular bisector is the XY plane. Okay, so what that means is any point xi plus yj is on the perpendicular bisector of this wire. Okay, so we're calculating on this plane at any point. All right, so let's take this point over here. Let's say, for example, let's take this point over here. And then, of course, we need to take a sample of the wire. So let's take this sample over here. That's my ds. And that's going to be dz in the k direction. Okay. My ds, if I take this sample over here, ds is the k direction. And the path element is dz. All right. If I take this to be my point over here, okay, which is, well, this is going to be r prime. This is going to be my r. The location of the point is r. This is my r, and this is my r prime over here. Okay, the position vector of this charge is r prime. The position vector of the point is r. So this is any point the xy plane. So my r is x in the I plus y in the j. Okay, so let's say this distance, let's call r perpendicular. Okay, this distance over here, this perpendicular distance from the wire. So this would be r perpendicular cosine phi in the I direction plus r perpendicular sine phi in the j direction. And this angle over here is phi. Okay, this is my x-axis. All right, that is r perpendicular cosine phi in the I direction plus r perpendicular sine phi in the j direction. We're talking about this point. How about r prime? Well, r prime is the position vector of this charge element over here, which is basically z in the k direction. Okay, the position vector of this one is z in the k direction. Do you see that? So we have ds to be dz in the k direction. The wire is going this way. This is the position vector of this point, which is the xy plane, because the xy plane is the perpendicular bisector of the wire that goes from negative b to b. Okay, and r prime is the position vector of this one. All right, now we can work out what we need. We're going to need r minus r prime, right? So let's do r minus r prime. My r, this one over here, r perpendicular cosine phi plus r perpendicular sine phi. Okay, so this is r perpendicular cosine phi in the I direction plus r perpendicular sine phi in the j direction minus z prime, I mean r prime. R prime is the position vector of the charge element, and that is z in the k. Okay, that's my r minus r prime. Okay, I mean, all right. And then of course I'm going to need the magnitude, r minus r prime. Okay, that's going to be square root of r perpendicular squared cosine squared of phi from this one, r perpendicular squared sine squared of phi from this one, and then z squared from this one. You see that? What's the sum of these two? Simply r perpendicular squared, right? So this magnitude over here, r minus r prime, is simply square root of r perpendicular squared plus d squared. Okay, so that's our distance. It's basically the distance from this point to this point. You see, this is z, this is r perpendicular, this is 90 degree over here. So it's just basically Pythagorean theorem. Okay, so that's my distance. And then I'm going to need the cross product. This is what I need. ds crossed with r minus r prime. Okay, we'll need this cross product. So ds, this positive element over here, this is straight wire, is dz in the k. Okay, so you've got dz in the k crossed with r minus r prime, which is this one over here. Okay, which is r perpendicular cosine of phi in the I direction plus r perpendicular sine phi in the j direction minus z in the k direction. Okay, so let's do the cross product now. What is k cross I?
J.
K cross I is j. So the first one would be, well, we have dz r perpendicular, and then I've got, okay, and then I've got cosine of phi over here. All right, cosine of phi. So k cross I is j. How about this one? K, I have k cross j. What's k cross j?
Negative I.
Negative I. Okay, so we have minus ds, and then I've got r perpendicular, and then I've got sine phi. Sine phi, and that is, okay, k cross j is, you said I, right? Okay. And what is k cross k?
0.
0. Okay. All right. So let's put this together. So you've got, let's factor this out. So this is dz r perpendicular. Okay, let me put this first. Negative sine phi in the I direction plus cosine phi in the j direction. Can anybody tell me what this is?
E theta or E
Very
phi.
good. E phi, very good. This is E phi, the tangential unit vector. Okay, so this is basically this unit vector over here, E phi. You take the circle, you take the tangent, that's E phi. So it's telling us the direction of the field is tangent to the circle of this wire. All right, so we have our cross product right over here. So you've got ds cross r minus r prime is simply, we've got dz r perpendicular E phi, dz r perpendicular, dz, r perpendicular, and e phi. Okay, so this is my my cross product. Now we can go to our integral. Okay, so the integral is, this is a formula, b equals mu naught current divided by 4 pi. Okay, and then integrate this, the integral of ds crossed with r minus r prime divided by the magnitude of r minus r prime cubed, right? So let's put in the values. So we've got mu naught current divided by 4 pi, the integral of, so this one is over here, this one, dz, r perpendicular, I can put it outside, but r perpendicular in the direction of e phi. Okay, and then this distance over here, you remember this distance, where the square root of r perpendicular plus d squared. Okay, so this is basically r perpendicular squared plus d squared 1/2 times 3. You got square root and then you cube it, you get 3/2. All right. So, oh, this is dz. I'm sorry, this is dz. So our integral is on dz. So let me simplify this. This is mu naught current divided 4 pi. So this two quantities are perpendicular if they don't depend on z. So that is, we can take them out. So you've got r perpendicular e phi. We can take this out. And the integral is dz over r perpendicular squared plus d squared 3/2. From where to where does z goes? Can you tell me? You see, the value of z goes from negative b to b. Do you see that? This is a wire. It starts negative b, goes to b. This is dz. So z goes from negative b to b. So this integral is going to be from negative b to b. Okay. Now all you have to do is do this integral. How do you propose you do this integral? Hmm?
Mm,
You have any proposal? Well, let's do it this way.
well, we could do double the integration from 0 to b.
Yeah, we can do that. It's not a big deal. It's symmetric. But let's do this one. I'm going to do this. You know, 1 plus tan square of theta is what? I'm going to use this formula over here. You see, you got this formula, cosine square of theta plus sine square of theta equals 1, right? If you divide both by cos square of theta, what do you get? Cos square of theta divided by cos square of theta divided by cos square of theta. Okay? This one is 1. And then this one is tan squared theta, right? And then this is sec squared, or 1 over cosine squared. This is sec squared theta, okay? So I want to take advantage of this formula, okay? So if I'm able to replace this by this, I can simplify it using this one, okay? So I'm going to start by saying let z equals r perpendicular times tan theta, okay? So I'm going to say let z equals r perpendicular times tan theta. All right. So what's the relationship between dz and d theta? This will be dz r perpendicular times the derivative. Do you remember what's the derivative of tan theta?
Secant squared.
Sec squared, right? Very good. So dz would be r perpendicular and then sec squared of theta. All right. So I have this one. And then let's simplify this one over here. This one, right? Maybe I put, well, let's simplify this. R perpendicular squared plus d squared equals r perpendicular squared plus r perpendicular squared tan square of theta, right? So we factor out r perpendicular squared, we get 1 plus tan square of theta, right? But that one is sec square of theta, right? Sec square of theta. So this is r perpendicular squared sec square of theta. All right. Now we have simplification, so we can write this integral again. So this b over here is mu naught I over 4 pi, And then of course, so we have the direction. The direction is E phi, r perpendicular E phi. Okay, we've got r perpendicular E phi over here. Now the integral, I have dz. Well, this is d theta over here. So r perpendicular sec squared theta d theta. Okay, and then this expression over here is r perpendicular squared sec squared theta, right? So we have r perpendicular squared sec squared theta cubed. I mean cubed like this. All right. So what does it simplify to? Well, let's simplify it. So this is mu naught over 4 pi I. Is this r perpendicular, was it over there before? Yeah, it's over there. Okay. So you got E phi over here. All right. So what do you have over here? This is sec squared cubed. Do you see that? Well, we have r perpendicular, and this would be r cubed, right? So you've got r perpendicular squared over here. Do you see that? You've got r perpendicular over here. From here, you get r perpendicular cubed. So it's going to be r perpendicular squared over here. You see that? We've got one r perpendicular. It's going to be cubed. So it's one r perpendicular squared. All right. How about the sec? This is cube, right? 2, 3 over 2 sec cube. So you've got sec squared divided by sec cube. That's 1 over sec theta. Okay. So this is 1 over sec theta d theta. Okay. But sec is 1 over cosine of theta, right? So this is just cosine of theta. Do you see that? Okay. So we have b equals mu naught I over 4 pi. And then we can simplify the r perpendiculars. So we've got one r perpendicular at the bottom, and then E phi. Okay, so you've got r perpendicular over here, and then you've got E phi over here. Those are the constants outside. Now the integral is basically cosine of theta d theta. Okay, now let's look at this limiters. Well, they were going from negative b to b for z, but we got to change them to theta. This is our formula. So we've got z equals r perpendicular tan theta, right? So that means theta equals z, well, tan inverse. Let's just say tan theta equals z over r perpendicular, right? And then theta is tan inverse of z over r perpendicular, right? So what is theta at b? Theta at z equals b is tan inverse of b over r perpendicular, right? And then theta at, you're right, we can do from 0 to theta and double it if you want. We can do that, but from negative b will be, this will be negative tan inverse of b over r perpendicular. Okay, so this is the integral. B equals, we have this constant over here, and then you've got E phi over r perpendicular. This integral goes from negative tan inverse of b r perpendicular to tan inverse of b r perpendicular, and the integral is simply cosine of theta. What's the integral of cosine?
Negative sign.
I think just sine, right? The root of sine is,
Oh yeah, I'm thinking backwards. Yeah.
it's positive sign. Okay. So we have the following. The b would be mu naught times current over 4 pi. We have direction, and then divided by r perpendicular. And then this is sine of theta going from negative tan inverse of, what's it? B over r perpendicular. Okay, b over r perpendicular to tan inverse of b r perpendicular. Okay, so let's calculate this one. Sine of tan inverse of b r perpendicular. How would you go about it? We can use this right angle triangle. Okay, so basically what we're saying is this is b, if this is b, if this is r perpendicular, this is tan inverse b over r perpendicular, right? So sine of this angle is this over this, and this angle is square root of r perpendicular square plus b square. Okay, so the sine of this angle is b over this. All right, so we're going to use our formula. So the b is going to be mu naught I over 4 pi e phi divided by r perpendicular, and then this is going to be b over square root of r perpendicular square plus b squared, and then minus negative is going to be plus. Okay, you see that there's a negative over here, so minus minus is going to be plus, so it'll just be twice like he said. So you've got r perpendicular square plus b squared. Okay, so we have 2b over here. All right, so we have, well, let's try it once again. Mu naught I hope I didn't forget anything, but e phi, and then we have over r perpendicular, and then we got twice of b divided by square root of r perpendicular squared plus b squared. Okay, so this would be the magnetic field at the perpendicular bisector of the wire. Okay, if you've got this wire at any point that cuts half, if you've got a plane that cuts half this wire, at any point in that plane, you can use this formula. Okay, at any point in that plane, where r perpendicular is the perpendicular distance between the wire and that point on the plane. Okay, now, how about the wire is infinite? If the wire is infinite, you see, any point is a perpendicular bisector. If the wire is infinite, any point is a perpendicular bisector. So for an infinite wire, it applies for any point, because for an infinite wire, you can assume that any plane is a perpendicular bisector, right? So let's simplify this for an infinite wire. Let's say magnetic field due to infinite wire. Magnetic field due to infinite wire. Now, as I've said, in this case, it's at any point, because for infinite wire, any plane is a perpendicular bisector, okay? So in this case, the formula applies for any point for infinite wire. And how do we do it? We just take the limit as b approaches infinity, okay? So this would be b equals the limit as b approaches infinity, okay? The length of wires from negative b to b, so b equals infinity of our formula. And our formula is mu naught I over 4 pi, and then we have the direction e phi over r perpendicular, and then we have 2b over square root of, is it square root? I guess, okay, square root of r perpendicular squared plus b squared, okay? Now let's do the limit. How do we do this limit? Well, let's take everything outside the constants. This will be mu naught I 4 pi e phi r perpendicular is a constant. Maybe we have 2 over here too, and then you have limit over b over square root of r perpendicular plus b squared. So how would you go about it? Well, let's factor out b first from this expression. Okay, so let me just do this one. So this would be, we can write this one as, this is b approach infinity, okay? We can write this as limit as b approach infinity. I've got b over here, and then I'm going to factor out b. You see, if I factor out b squared, that's b. So it'll be square root of, this would be r perpendicular over b squared plus 1, okay? Then you see, this goes out, b by b. This goes to 0 as b approaches infinity. So you just have 1 over here, right? As b approaching, this goes to 0, we have this 1 over here. All right? Do you see that?
Yes.
This b cancels out. As b goes to infinity, this goes to 0. We just have 1 over here. So just 1 over here. All right? So this just goes to 1. This goes away. This goes to 1. So we have the following formula. Mu naught I, you see this 2 over 4 pi would be 2 pi. Okay, this is 2 pi. So you've got 2 pi r perpendicular, and the direction is E phi. This is the magnetic field due to an infinite wire. It applies anywhere because any plane is a perpendicular bisector for an infinite wire. Okay. There's a simple way of deriving this formula, we'll see it later. For symmetric charges, for symmetric currents, just like Gauss law, there's a law that helps us to do this stuff very easily, but we're going to do that in the next section. Let's see. I've got on section. Oh, all right. So what does this mean? You got this wire over here that extends in all directions over here, and then the magnetic field lines are going to be circular. Okay, so the direction is E phi, like this. The magnetic field lines are circular because it's tangential. All right, and if the current is counterclockwise, then the direction is going to be, if the current is positive, it's going to be counterclockwise. This is E phi right over here. So if the current is counterclockwise, I is positive. If the current is clockwise, make it negative, it's clockwise. Or you can use the right hand rule. You see, if this is current, you get field counterclockwise. If the current is down, you get field clockwise. Okay, so what you do is you make I positive if it is counterclockwise, you make I negative if it's clockwise. Or if you want, you can just do the magnitude of this one and then do the right hand rule direction. Okay, this is counterclockwise, you get up. If it's clockwise, you get down. Okay, so that's how this formula works. Maybe let's do an example for this one. Example. All right.
The paper's drifting again.
Sorry. So in this case, let's assume the wire is, the direction of the current is, let's say, perpendicular to the paper. Okay, this is a current. Let's say this is I equals 2 amps. Okay, and then let's say we want to calculate the magnetic field over here, maybe. Okay, so we know the magnetic field lines are circular because the direction is tangential. Okay, and so that's the magnetic field line that goes around the wire over here. Okay, so let's say the radius is 3 meters. All right, and we've got current. So let's say this is point P. The question is calculate the magnetic field at point P. The magnetic field at, maybe let's say A at P, okay, at point P. All right. So, and we need the, well, this is perpendicularly out, perpendicularly in over here, okay? So the magnetic field, first let me use the formula and then I'm going to the right hand rule, okay? So this is mu naught I over 2 pi r perpendicular, okay? In the direction of E phi. All right. Now, is the direction of the current positive or negative? It's negative K. This is a cross. The direction of the field is of the current negative K. So it's going to be negative. All right. So we're going to say I equals negative 2 because clockwise. All right. And what's E phi over here? Can you tell me? E phi is in a counterclockwise direction like this. So what's the value of E phi over here? Can you tell me?
Pi?
No, I is to the right. This is left. You see, counterclockwise to the left. So it's negative I, right? So E phi at this point is negative I. And the current is negative 2. All right. So this is B equals mu naught. And the current is Oh, actually, my direction over here is counterclockwise. I thought I made it clockwise. I meant this way. Okay. So we're assuming clockwise direction. I made it this way. Okay. So this is the direction of E phi. It's still negative I. You go counterclockwise, you get negative I. So if I negative I, but the current is also negative 2. Okay. So we have negative 2 over here, and then 2 pi times the radius, 3, and then my E phi is negative I. Okay? So what do you get? You get mu naught over 2 pi, and then you got 2 over 3 over here. And the direction negative, negative, positive I. Okay? So let's look. This is it really I? You put your, this is clockwise. I'm confused. This is the current. Okay, so we have E phi going negative I and the current going negative 2. So the direction is the direction of the field. No, this is the field. I'm thinking of this as current. Let me do it again. Okay. All right. So if you use the right hand rule, this goes down. The field is this way. Do you see that? This is a cross. So I put this over here. It goes this way. So we know that the direction of the B over here is I. The direction of the field is I. Okay. So I'm trying to use this formula, negative times negative 2, you also get positive I. Do you see that? I'm trying to show you both are the same. If you use the right hand rule, you put like this. So the direction of the field is this way from the right hand rule. So this goes this way. This is E theta. E phi is also, but the field will be this way. Okay. So at this point, the field will be in the I direction. All right. So what you can do is, if you want, you can just do the magnitude. You put this in absolute value, and then you do the direction from the right hand rule. You can say B equals mu naught over 2 pi. What is that? Current perpendicular. Okay. You put an absolute value. Okay. And then you do the direction using the right hand rule. If this is current, this is field. Okay. So if it's counterclockwise, you go up. If it's clockwise, you go in. All right. But generally, this this direction would be related to the right hand rule. All right. So this section, we're going to look at the magnetic force between two power wires. Magnetic force between two parallel wires, between two current carrying power wires. Current carrying parallel wires. Okay. So suppose we have these two wires like this. Let's say they're carrying current in the same direction, like this. Okay. Let's call this wire 2. Let's call this wire 1. So what's going to happen? This has its own magnetic field, right? That magnetic field is going to exert force on this one. All right. So we're going to get an expression for that force. Okay. First, let's find the magnetic field due to this one at this location over here. Let's call this distance, maybe this vector d12 as position vector of 1 with respect to 2. Okay, let's call it d12. All right. So what's the field due to this wire? Well, we just got a formula for it. It's a straight line. We're assuming infinite direction over here. Okay, it's going to be mu naught over 2 pi I over R perpendicular in the direction of E phi. Okay. So this is going to be the current going this way. So the direction of the field over here is going to be what? It's going to be perpendicularly in, right? You got the current going this way. You got this one going perpendicularly in. Maybe it'll be this negative K direction. All right. Now you got that magnetic field. This is b on 1 by 2, okay? But this wire 1 is in the field of this wire, right? So because of that, there's going to be force. You remember the formula for the force? The force is IL cross B. You remember that? So we've got this field crossing with this one. Now, well, this is DC current will be I2 over here, and this will be I1 over here. So we're going to take a certain section length over here. So let's obtain the force is this one. So we've got FB. Well, the angles are 90 degrees, so let's have IL B12. All right. And B1 is this one. So you've got L, I1. Let me put this one. Well, I've got L, and then mu naught over 2 pi. You've got I2, you got I1, you got R perpendicular over here. Okay. So this would be the magnitude of the force. Now let's look at the direction. You see, the magnetic field is this one, would be perpendicularly down. Okay, that is the magnetic field. How about this is the direction of the current is up. Okay, so you got the following. You've got over here, you got current going this way, you got field going down. Okay, so if you put your screw over here, rotate this way, it'll go this way towards the other way. Okay, so if you do the right hand rule or screw rule, you will see that the force actually goes this way, the magnetic force. The magnetic force, okay, and it's action reaction. So this also will attract this one. So the conclusion is if the currents are in the same direction, they attract each other. Okay, if the two wires are carrying current in the same direction, they attract each other. If they're carrying current in opposite directions, they repel each other. Okay. Oh, it's already 4:09. Let's take 5-minute break and then we'll do the next one. Okay. Let's take 5-minute break. All right. So we're looking at the force between two parallel wires over here. So we see that if these two directions are the same, the force is going to be attractive. And they're going opposite, is going to be repulsive. Okay, usually similars repel, opposites attract, but in this case it's different. If they're similar in the same direction, it's attraction, they're going to attract each other. And if they're carrying currents opposite direction, they're going to repel each other. Okay? So let's go to the next section, which is on Ampere's law.
Oh, could you move the tablet a little bit?
Oh my God. I should look at my computer often, I guess. So the next section is going to be on Ampere's law. Okay. This is one of the important laws in electricity and magnetism. There are 4 of them. They're called Maxwell's equations. Okay. The first one is the Gauss law that we saw. Okay. And the second one, I'm going to do the other 2 later on. Okay. But this law is based on line integrals. So first, let me do a little bit integral. The line integral of magnetic field. The line, it's just like work. You remember, work is a line integral of magnetic field. So let's say you have this path over here. You got this magnetic field over here. Okay. So what you do is you take a certain path over here. Let's call that ds. Okay, this path element over here. And then you take a component of this magnetic field in this direction. Let's call that b parallel. Okay. The product of these two, b parallel times ds, represents the value of the line integral for this small path over here. Okay. So you have this small line integral, let's call L, would be b parallel times ds. Okay, and then you simply add up everything. So be the line integral from here to here. Okay, so the line integral will be the integral of B parallel times ds. Okay, but what is B parallel? If this angle is theta, if the angle between ds and the field is theta, then B parallel is B times cosine of theta, right? So this is basically B times ds times cosine of theta. What kind of product does this remind you? Cosine.
The dot product.
Dot product, right? So this is B dot ds. All right. So this expression is basically B dot ds. So the line integral is the integral of B dot the path element ds. You remember work? Work was the line integral of force. Okay, we use a dr for the path element, but this is the work is the line integral of force. Now we're talking about the line integral of magnetic field. It's the same thing. Okay, so this is what we call the line integral of magnetic field. All it is, you take small path element and then take the component of the field in the direction of the path element and then you multiply them. Okay, and if you do that for all the paths, you add them together, you get the line integral, which is simply like similar like the work is the line integral of force. Now we're talking about the line integral of the magnetic field. Now let's simplify this. B is a constant. If B is constant, you can take it out of the integral, right? Because that's what we're going to use most of the time in this course. So if B is a constant, then the integral becomes like this: B dot ds integrated, let's say, from initial position vector to final position vector. Okay, maybe I'm going to call this is like dr. So it's going to be B rf minus ri. You see that? This is the position or displacement delta r. Okay, so for a constant field, the line integral is simply the dot product of the magnetic field and the position vector delta r. Now look, it doesn't matter what the shape of the path is. Let's say that's what you have. If you're using this coordinate over here, this is your Ri, okay? This is your Rf. Delta R is this one. So it doesn't matter what the shape of the path you're looking at. Delta R is simply the vector connecting the initial point to the final point, okay? So it doesn't depend on the shape of the path if you're dealing with a constant B, all right? So this is the formula for a constant magnetic field. And of course, you can use the definition of dot product, will be the magnitude of the field, magnetic of delta R times the cosine of theta. If theta is the angle between the displacement and the magnetic field, okay? So this is what we call the line integral of the magnetic field. Now, Ampere's law says, if you evaluate this on a closed path, that is proportional to the current crossing the path, okay? So let's say you take this path over here. If you evaluate this integral on a closed path, you know, magnetic field is produced by current, right? So if you do that for this closed path over here, Ampere's law says that integral is directly proportional to the current that crosses this path perpendicularly. Okay, so let's state Ampere's law. Ampere's law is said the line integral on a closed path, the line integral of the magnetic field, on any closed path, is proportional to the current crossing the closed path, to the current crossing the closed path. Okay, let's try this mathematically. So let's say I have this path over here. You take ds over here. You take magnetic field over here. You take the dot product. the add up all of them in a closed paths is proportional to the current. Okay, so this is Ampere's law. If you take B dot ds and evaluate the closed paths, we're going to the line integral in a clockwise direction. That equals mu naught times the current crossing the loop. This is Ampere's law. Okay, if you evaluate in a closed paths, then that is proportional to the current. And of course, mu naught is the constant we have already used it, which is 4 pi times 4 pi times 10 to the power of -7. Okay, so Ampere's law says if you do the line integral closed paths, that is proportional to the current crossing that path. This is a hypothetical path. This is just this field over here, and you choose any path. Actually, you choose that path in a way that's easier to calculate, but it can be any path. And that path is proportional to the current crossing the path. Okay, so let's consider an example for this one. Example. All right. Suppose this is the path I want to calculate the line integral. Let's say this is the line integral. Let's say this is my axis. This is my x-axis and y-axis, okay? Let's say it's my y-axis. Let's say this my x-axis. So let's say b equals maybe, let's say 4 in the I if y is greater than 0. And let's say maybe negative 8 in the I if y is less than 0. Okay, we have this field. So on this place over here, above this axis over here, B is this way in the 4i direction. Okay, but at the bottom below the x-axis, B is this way, it's negative 8i in the direction. Now the question is, calculate the current crossing this rectangular path. Okay, this field over here is produced by a current. So there must be current producing this field. So we want to obtain that current, okay? So the question is calculate the current crossing the paths. Crossing the paths. Okay? So what we're going to do is evaluate the integral. Okay? So maybe let me give names to this ones. Let's give this names. Let's say it's A. Let's say this is B. Let's say this is C. Let's say this is D. Now you have to do the integral in a counterclockwise direction if you want to use the right hand rule. That is, if the field is counterclockwise, the current is up. If the field is clockwise, the current is down. If you want to use that rule, then you have to make sure you do the integral in a counterclockwise direction. All right. So we're going to do the integral for these different paths. All right. So we have, well, I think I'm going to need numbers over here. Let's say this is 2. Let's say it's -2. Let's say this is -4. Let's say this is 4. Okay. All right. So the formula we're going to use is this one. B dot ds evaluated in a closed path, evaluated in counterclockwise direction equals mu naught times I. Okay. So we're going to calculate this one divided by mu naught. That'll give us the current. All right. So that's the goal. So I'm going to separate it in 4 different parts. So this one over here, B dot ds. Okay. First, I'm going to do an AB. On path AB. Okay. B dot ds. And then I'm going to do on path BC. Okay. And then I'm going to do on path CD. Okay. B dot ds. And then back to A. Okay. Integral of B dot ds. And no, this is plus CD, I'm sorry. And this is dA. All right. So we can calculate these 4 integrals. That will be a closed path. I'm going now in a counterclockwise direction this way. Okay. So let's look at what do you think is the line integral on this path? You see the magnetic fields are to the right or to the left. All right. So what do you think is the paths and the field are perpendicular on this line? The path is this way, the field is to the right or the left. So the line integral is 0 on these two path elements. Okay. So on DA and CD, the line integral is 0 because the paths and the field are perpendicular to each other. Okay. So we can just put AD and BC to 0. So AD, AB, BC. So this one is 0. That's this one over here, and this is also 0. This one is 0. The reason is the path element and the field are perpendicular to each other. Okay, the field is to the right and it's vertical. So we just have these two. So we can write again. You've got AB, that ds, okay, and then the other one is going from C to D. Okay, C to D, C to D, P dot ds. That's all I have to do. Now, remember our fields are constant, so I can use the formula B dot delta R, okay? So this one over here is B dotted with this position vector over here. Okay, this is my delta R for this one, which is, it goes from -4 to 4, that is 8 in the I. This vector over here is 8 in the I, right? So that is, let me say, delta R IB over here. And this is going to be B dotted delta R for CD, okay? Delta R for CD, all right? Now, on this, below the x-axis, the field is negative 8I, right? So we have, for this one, I have negative 8I dotted with, and delta R IB is this one over here. This is a vector from A to B, which is from -4, which is 8 in the I direction, okay? So this one is 8 in the I direction, all right? Plus, now, this is 0, we're looking this path. Now you see, I'm going this way in a counterclockwise direction. This is my position vector right now, okay? And the field is 4 in the I direction, all right? So the field above the x-axis is 4 in the I direction. Now the position vector, I'm going this way, is this one, is -8 in the I direction. This is a position vector over here, okay? So this is -8 in the I direction, okay? So that's it. So you've got I dot I is 0, so you get -64 over here. And then over here, we have 4, that's -32, right? This is in the I, minus, well, there is an I as well. So it's -32. So we get -96, okay? All right, so you got this formula over here. That's what we have. B dot ds equals mu naught I equals -96. Okay, we just calculate this one on a closed path. All right, so the current is -96 over mu naught amps. Okay, what does the negative mean? It's perpendicular.
Clockwise.
The direction is the direction of the current is perpendicularly in. It's negative. All right. So direction of current is perpendicularly in. Direction of current is perpendicularly in because, well, the integral is 0. Okay. All right. So do you get the idea? It's just like Gauss law. You remember Gauss law? You do the surface integral on any surface, and that tells you that's proportional to charge inside. The only difference is the line integral. You take any path, the value of that path tells you how much current is crossing that path. Okay? So that's what we call Ampere's law. Let's look at another example. Suppose we have, let's say, we have the following wires. Let's say this is 1, 2, 3, 4. let's say I have over here a dot. Let's say all the currents are carrying 2 amp current. Let's say all the wires are carrying 2 amp current, okay? So let's say I have a crossover here, I have a crossover here. At 4, I have a dot, a -1, I have this one, I have -2, maybe I have a cross and so on. So the question is, calculate the net current crossing this path. How would you calculate it? Now we're calculating the line integral on this path, okay? But we know the currents. You see, these are the currents. So the total current crossing this path is this one over here, okay? So you've got -2 over here going down, 2 going up, 2 going up, -2 going in. So what do you think is the line integral on this path? Okay,
0.
well, the question is calculate this one. That's what we're looking for. .ds question mark. That's what we're trying to calculate. Okay, but we know that this equals mu naught times the total current crossing the path. What's the total current crossing the path?
It looks like it's 0.
0. You see, you got -2, 2, 2, 2. Okay, so the total current is -2. The next one is +2, +2, +2, -2, 0. So this line integral over here in this case is 0. Okay, .ds equals 0. Okay. Now the main use of this formula is to help you obtain the magnetic field due to symmetrical currents. Okay, just like Gauss law helped us. You see, in Gauss law, there is an integral for calculating the electric field, but that's a very difficult integral. Okay, but for symmetrical charges, we can use Gauss law to obtain the electric field very easily. The same thing over here. If you've got symmetrical currents, then you can obtain the magnetic field very easily using this law. So that's what we're going to look at now. We're going to look at some examples, okay? First, we're going to look at field. We have already done this using integral in the last section. Field due to an infinitely long straight wire. Okay, first we're going to write symmetries from conclusion. Conclusions from symmetry. Conclusions from symmetry. Okay, now suppose you have this wire over here. Okay, if you take a concentric circle over here, there is no reason why the magnitude on the points in a concentric circle should be different, because they're subject to the same conditions. Okay, so one conclusion we can make is that the field is constant on a concentric circle, on any concentric circle. Okay, that's one observation we can make from symmetry. And the other one is about direction. From symmetry, we can conclude that the direction of the magnetic field is tangential to a concentric circle. Okay, so the second conclusion we can make from symmetry is direction of the direction of the field is tangential to a concentric circle. Okay, so we're going to use these two conclusions from symmetry to obtain the magnetic field. All right, so now suppose I have this wire over here. Okay, so let me take my my path to be this one over here. Okay, concentric circle over here. All right, so let's say the current I is going this way over here like this. All right, so first let's do, well, we have this integral equals mu naught times the current. Okay. Now my goal is to get a formula for the magnetic field. All right. So the magnetic field is a constant, right? So you can take it out. So you've got, well, first let me repeat that is. The magnetic field is tangential. The ds is the same direction. Okay, so beta ds, they are either parallel or opposite because they're both tangential. Okay, if you take a circular path, ds is tangential to the path, and from symmetry, we've concluded that the magnetic is also tangential to circular paths, right? So that means that this one is bs times ds. This is a component. It will be positive if it is counterclockwise, it will be negative clockwise, but the angle between them is either 0 or 180, right? So let's write it this way. So this integral is bs times ds over here, okay? Now, the magnetic field is a constant from conclusion of symmetry. So this one is bs times ds over here. That equals mu naught times I. What do you think is the integral of ds evaluated over the whole path? If you add up all these ds's together, what do you get? Let's say this is R perpendicular, huh? Circumference, right? If you have a circle and you add all the ds's, you get circumference, okay? And the circumference 2 pi R perpendicular. All right? So we have the magnetic field times 2 pi R perpendicular equals mu naught times current, okay? And we have already concluded the direction is E phi. So you've got bs is mu naught I 2 pi R perpendicular. You see, we have already evaluated this using a long integral, but this one you can obtain very easily. All right. So this gives you the component, and then you can add E phi for the direction. Okay. So the magnetic field, as we just saw before, is mu naught I divided by 2 pi R perpendicular in the direction of E phi. Okay, the current is positive if it is counterclockwise, negative if it's clockwise. Okay, we have already derived this in the last section, but now we're able to do it very easily using Ampere's law. Okay, and next we're going to look at magnetic field due to a solenoid. Magnetic field due to a solenoid. Okay, so a solenoid is a coil like the one we saw in the lab last time. Okay, this is what you call a solenoid. You have something like this, and then you get something like this. You got coil over here. Okay, that's what you call a solenoid. All right. So first, we're going to write conclusions from symmetry. Okay, the magnetic field in a solenoid looks something like this. It's approximately constant inside, but is approximately 0 outside. Okay, so we can say the magnetic field is approximately constant inside. Magnetic field is approximately constant inside, approximately constant inside, okay? And the field is approximately 0 outside. The field is approximately 0 outside, okay? And this direction is parallel to the axis, you see? This direction is parallel to the axis. So the third conclusion we can make is its direction is parallel to the axis inside. Its direction is parallel to the axis inside. Okay. Now with this, we can get an expression for the magnetic field. So let me take my path to be this way. First, I'm going to assume n to be number of turns. Okay, and this would be the length of the solenoid. Okay, so I'm going to take this path now to do Ampere's law. I'm going to take this path over here. Okay, now look, we're going to do the line integral on a closed path, right? First, let's look over here. This path over here. This path is perpendicular to the magnetic field. Okay, so the line integral is going to be 0 over here. It's going to be 0 over here. And this line is outside. Outside the field is 0. So the magnetic field is 0 over here too. The only contribution comes from here. Okay, this is perpendicular to the field. This is outside where the field is 0. So we get contribution only from this one. And the magnetic is constant. So it's just going to be the magnetic field times the length. You see that? So we get contribution only from the line inside. So you've got this one, B dot ds equals B times L, okay? This is contribution only from the inner line, contribution only from the inner horizontal line, from the inner horizontal line, okay? So now let's go to this one, mu naught, this one over here, which we find out to be Bs times L is equal to mu naught. Well, there are n number of terms. I'm going to put over here, I over here. So you see, this is a formula. Mu naught, number of turns times current divided by the length. This is a formula for calculating the magnetic field inside a solenoid. Okay, and the direction of the field is the direction of the area of the loop. Okay, and the current and the field are related by the right-hand rule. If the current is counterclockwise, it will be to the right. If the current is clockwise, it will be to the left. Okay, so let's say direction of current and field. Current and field are related by the right-hand rule. By the right-hand rule. Okay. All right. So these are a couple of examples how Ampere's law helps us to get formulas for magnetic fields. Okay. Now let's look at modifications of Ampere's law. Modification of Ampere's law. Now Ampere's law was obtained experimentally by Ampere. Okay. But Maxwell, the guy who organized all electricity and magnetism, when he was writing equations, he noted that the law is actually not consistent. For the law to be consistent, there should be an additional current that he called displacement current, okay? And so in addition to the normal current that travels through wires, he added a new kind of current called displacement current, okay? So Maxwell added a new current called Ampere's law, called displacement current. Displacement current to Ampere's law. So he wrote it this way. So if you take the line integral on a counterclockwise direction of the magnetic field on any path, that equals mu naught times the current, this is the normal current that goes through wires, plus a displacement current, okay? And he found out that this displacement current is proportional to the derivative of the electric flux with respect to time. He found out that this has to be the derivative of the electric flux with respect to time. Okay. Now, a very good example of displacement current is the current between the plates of a capacitor. Okay. Suppose you have this capacitor. Let's say it's a positive terminal. This is a negative terminal. All right. Now, if you connect this, you're going to have a continuous current through this wire. But is there a break over here? This is a normal current that we know of. But what happens in between these two? Let's see what happens. Now, this plus and this negative, you got dielectric over here. What's going to do? It's going to pull the positive and the negative apart. Okay, let's say this was like before. But when you charge this one, The positive will go to this end, the negative will go this end, right? Now, what happens when this current decreases? When the charge goes over here, the electric force decreases, right? So this gets smaller and smaller, smaller and smaller as the field decreases. So basically the movement of charges, you see, they were extended very far away from here, but when charge moves, the field decreases and the charge gets closer because the force decreases. So that's movement of charge. Do you see that? The molecule was pulled apart. But if charge goes away from the capacitor, the force decreases and they get back together. So that's another kind of movement of charge. So it's that kind of movement of charge that Maxwell calls displacement current, okay? Actually, what he was trying to solve was a very simple problem, what you call the continuity equation. You remember when we did Kirchhoff's law, we said current that goes in equals current that comes out, okay? How about if you apply that over here? You've got current that comes out, but there is no current over here. It doesn't make sense. That's the problem he solved. If you say there is no current over here, then the continuity equation fails. Current can come out of nothing. If it comes out over here, it should come in from here. That's how he figured it out, okay? So he simplified this formula like this. So let's write it. So this is Ampere's Maxwell's equation. Ampere's Maxwell equation. So you take the line integral on any closed path, and that equals mu naught, the normal current that flows in wires, plus epsilon d phi e by dt. Okay, this is Ampere's Maxwell equation with a correction from Maxwell. Okay, now we can actually show that for a capacitor, this is actually equal to this current. Okay, so let's try to do that. What is phi e? Phi e is electric field times area. Okay, you take this capacitor, the electric times area will give you the electric flux over here. But let's calculate the electric field. You see the field outside is 0. Okay, you can use Gauss law over here. So over here is 0. Over here, what is it? You've got E times dA over here. E times dA equals charge density, sigma, times the area A. And there's epsilon over here. So the electric field is actual charge density divided by epsilon, right? So the flux is this charge density over epsilon times area. What is charge density? Charge density is charge divided by area, right? So you get, this is charge divided by area, and you've got epsilon, you got area over here, this goes away. So you get, this is simply charge, charge divided by epsilon, right? So what is the derivative? d phi e by dt is simply 1 over epsilon times the derivative of the charge, okay? That's d phi e by dt. I put that over here, you get the normal current. Do you see that? So the displacement current, this is the displacement current, is epsilon d phi e by dt. But we show that the derivative d phi e by dt is 1 over epsilon dq by dt, right? So you see the displacement current is actually equal to dq by dt. What's dq by dt? Charge, okay? So the current does not break inside the capacitor. It continues with the same value, all right? So it's about 5. There's only one section left. I think I'm going to include it in the next chapter, okay? It's about 5 right now, all right? So do you have any questions? I know this was a long lecture, I'm sorry. But do you have any questions so far? All right, then I'll see you on Tuesday, and we're going to work on the classwork for this one on Tuesday. All right. Bye-bye.
Thank you, Professor.
Bye-bye. See you.